Hello everyone, welcome to this video. My name is Amir Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm gonna show you how to do MODIS sharpening for the LST data. In my YouTube channel, the MODIS sharpening technique for NDVI data already published, and most of you certainly know about the sharpening techniques using regression analysis in the Google Earth Engine platform. But in this tutorial, I'm going to use the same strategy for the LST data downscaling. That could be very useful. As you know, MODIS LST product provided 1 kilometer spatial resolution, but through the combination and the data fusion and regression analysis, we can improve its spatial resolution from 1000 meter to 100 meter, thanks to making a relationship between MODIS and the Landsat LST data. Now, in this tutorial, I'm going to show you how to produce daily LST data with 100 meter spatial resolution. As you know, Landsat provided LST data with 100 meter spatial resolution, but the limitation is temporal resolution. Landsat data only available each 16 days, but MODIS data is available daily. So, through the regression analysis, we can have both of advantages, the daily temporal resolution and the higher spatial resolution. That could be done through the regression analysis in the Google Earth Engine platform. So let's go to the code editor environment in the Google Earth Engine. In the first step, identify region of interest through the drawing tools available here. In the previous tutorial, I showed you how you can also define your region of interest through the FAO boundaries in the Earth Engine. You can subscribe the channel and see the other videos to get more information about satellite data processing in the Google Earth Engine platform. In this tutorial, I'm gonna select a part of northwestern of Iran. It's a farmland, and I'm gonna produce daily LST data with 100 meter spatial resolution. All of the data I'm using is publicly available, and you can use this tutorial for all around the world, and there is no limitation. So, through a drawing tools here, draw a rectangle. For example, I'm gonna select agricultural area in the satellite view. That's what it looks like. So, after selecting region of interest, to have a focus on the region of interest, use map.center-object. As the region of interest, or ROI, already known as a geometry, map.center-object geometry allowing to have focus on the study area when the code is running, just like that. In the next step, we need to call Landsat and MODIS LST data separately with two different variables. Make a new variable for Landsat equals to, through the search places and dataset, call Landsat 8 collection 2 level 2. Landsat 8 collection 2 level 2. So, all of the available data for Landsat 8 collection 2 listed here. The tier 1 data is the target data imported into the code as an image collection. So, assigning the image collection to the Landsat variable, and then define the filter bounds and filter dates to restrict your data to the temporal period you want to study, and also to the region of interest you are working. Through the filter date, identify the time start and time end. We are actually spanning our data to a specific period of time. What does it mean, time start? The acquisition date, a start date and end date. For the regression analysis, would be better to set a long period of time to make a stronger relationship between dependent variable and independent variable. So for example, I'm gonna select whole period we have since 2013, since the date Landsat 8 data are available to present. The Landsat 8 launched at 2013 and the time end equals to, for example, I'm producing this video, I'm making this video in 2024, and so the time end should be 2024 in this tutorial. You can also select longer and also the smaller period of time regarding to your application, because I need to have all existing data, cloud-free ones, in the regression analysis to make a strong relationship. That's why I'm selecting a longer period of time. Got filter bound, bounding the data according to the region of interest. Filter bound is really important when you are working with Sentinel data, with Landsat data, because Landsat and Sentinel both have framing structure, and when you are working, it is important to set a boundary of region for the further analysis, to bounding your data to a specific region of interest first. So that's what we are doing in this step. For the next step, I need to select the land surface temperature band from collection to level 2 data. The main advantage for this product is all of the surface reflectance data atmospherically corrected, and for the thermal infrared band, land surface temperature already calculated. And you don't need to calculate the LST same as what we have done before, So just here, you need to call the LST data and apply a scale and factor, and then make a regression analysis. And you don't need to struggle with the LST calculation process anymore. That's why we are using Landsat 8 collection to level 2 products. So then here I need to set some filters before go through the LST bands. As I need to use cloud-free images, it's very important to filter the data based on the cloud cover. So here, let me show you some property information we have in the Landsat. For example, one of the Landsat data selected through the first one according to the acquisition date, because I need to show you what kind of properties available here. The properties is something like metadata file that all of the relevant information for each product already gathered and also printed here, helping us to filter our data based on different properties available here. One of the important information here is cloud cover. For example, the first image including 81% cloud coverage that doesn't work in our case. So to avoid uncertainties, we need to use those of images with the lower cloud cover, and also we prefer to use cloud-free images. So accordingly, I can make a cloud cover filter to call those of images in which cloud cover is less than 10%. For example, here I'm making another filter, earthengine.filter.lt. The LT means the less than. Two arguments we have for this filter. The one is name. Here could be the cloud cover as a property. Copy and paste it. And the next is the value. It has a numeric format. So, and now I can set number 10 to call those of Landsat data in which cloud cover properties has a value number 10 or less than 10, because this is LT or less than. So the 10 not included in this filter. The values lower than 10. In the next step, after doing this, we need to call and select the surface. We need to call LST data and also extract it and return it as a final band in the next step. As you can see, for each data, we have 19 elements, 19 bands available for each date. And the target band I'm going to work is ST band number 10. The ST stands for surface temperature. If you go to the data properties, you can get more information in this regard. So here, the data description is available through the bands. You can see that the ST is clearly the surface temperature band for the collection 2 data. And also, as you can see, we have one scale and one factor that should be applied on each band, on each surface temperature band we have during the time period. Back to the code, and if you check the data properties, you will see that the scale and factor values in the properties also available. For example, here we have temperature add band. This is the offset value. It is 149. And if you go to the data description, the offset value is 149. And also the scale value is 0.003. And then here you can see that the temperature mode band or the gain value is 0.003 again. So meaning that we can get the scale and value from the properties and apply them on the surface temperature band. It's very, very easy technique. So now in order to select the surface temperature band from each date and apply a scale and factor, we need to make a loop through the map helping us to make a loop over the data that's already imported through the Landsat variable. In the loop, I need to apply a specific equation or a specific procedure through a new function in which each input image considered as IMG or named as an IMG. You can choose any other names you need. So here, now make a new variable as TIR, thermal infrared, equals to img.select, allowing us to select the target band here. The target band is band number 10 or STB10, just like that. Copy the band name and paste it into the code. So in the next step, we need to get the gain and offset that is available here in the properties. We have the add band ST band 10, and also we have mult band ST band number 10. So here a variable for TIR gain equals to apply on TIR band, or no, before that we need to get the target properties. That's here is the mult band. Whenever you want to select something from your metadata or from the properties, you need to use get. And whenever you want to select a band or image, select will be useful. So to convert the properties from the string to number structure, I'm using EarthEngine.number, just like that. So then you need to repeat the same variable, but this time for the offset parameter. Offset equals to EarthEngine.number. As you can see, copy and paste it. The only thing changed here is the type of the property we are working. Instead of mult, we have add band, the offset value. So after the gain and offset extracted from each TIR image in each date, we need to apply these values on the TIR bands. So here we have a LST equals to get TIR image first and multiply TIR gain coefficient and add it to the TIR offset value. Finally, the function returning the LST band, it is calculated before and a scale and factor applied on with the properties of input images, specifically system time start and system time end. From now on, in the rest of the code, we don't need to the other properties. The only properties we need for the next step is a system time start for the time series analysis. That is very, very important. And also would be good if you have system index too, because the system index explaining the system time start with a simpler format and also a part of it explaining the time, the acquisition date in which the satellite data is taken. So in addition to system time start, we can have system index 2, just like that. And now print the new results to see how many Landsat data is available after doing this process. As you can see, we have 404 images in which cloud cover is less than 10% for the selected region. But remember that Landsat data has framing structure, and also before further analysis, you must be sure that your area is completely covering in the paths and rows that are tracking your region of interest. In order to know or get information which path and row covering your study area completely, the easiest scenario is go to the Earth Explorer website. The Earth Explorer is the main website created by collaboration between NASA and USGS that helping us to get Landsat data from easily, and also this is the main hub that's releasing Landsat data from Landsat 1 to Landsat 9 that now is under operating. So the only thing you must to do in this website is select your region of interest. For example, my region of interest is this location that's already focused on this region because I was working in this website before. That's why my region of interest already shown here. But depends on your region of interest, you can have focus on different region and select your region just like what I have done. So no need to change anything else, just go to the data selection. In the data sets, go to the Landsat collection to level 1 and also select the Landsat 8 or 9, the satellite data you are working with. Then go to the results and waiting for the results. As you can see, various frames available in this region. The frame with pass 168 and 34 is the target frame that's completely covering my region of interest. That's why I need to actually call those frames with pass 168 and rows 34. So back to the code again. We can limit our data to a specific path and row throw the equal filter, earthengine.filter.equals. The property for pass and rows is WRS pass and WRS row. WRS pass 168, then .filter earthengine.filter.equal. This time WRS row equals to, what was that? It is 34, because we need to have data that's completely covering our study area. This is the 34. And run the code again, and as you can see, this time we only have 119 elements for this specific pass and row in which the cloud cover is less than 10%. So, after the Landsat data collected and filtered and LST calculated for, now we need to call Landsat, MODIS daily LST images. Make a new variable for MODIS data equals to, again, same scenario. Go to the search places and dataset and type MODIS temperature. As you can see, different products listed here. One of them is Terra land surface temperature with 1 kilometer spatial resolution. Import it into the code, and also you can see this as a second image collection that is assigning to the MODIS variable. Again, we need to have a filter date exactly for the time period in which Landsat data collected, because for the corresponding dates between Landsat and MODIS, we need to join this data. We need to find corresponding dates for the times Landsat and MODIS both available to make a regression relationship. In such kind of relationships, it is very important to have the data in the same dates. That's why we need to have same time start and same time end. This is the first condition. Time start and time end. No need to have filter bounds for the MODIS because it is coarse spatial resolution product, and also it has no framing structure such as we have in Landsat product. But here we need to make a function to select the target LST band in the MODIS variable and then apply the scale and factor if there is a scale factor for MODIS temperature data. To make a function, use the map, and also to make a loop, we're using the map, and then throw a function each input image from MODIS data named as an IMG, and now make a new variable as TIR. But TIR or the LST. LST equals to, from each input image, select LST day with 1 kilometer. If you go to the data description for the MODIS product, you will see that the daytime land surface temperature band name is LST day 1 kilometer. And also the unit is Kelvin, but only we have a scale and the offset is 0. The scale is 0.02. It's very simple. So just throw dot multiply, just like that, 0.02, apply it on LST day with 1 kilometer spatial resolution. So in the next step, function returning the calculated LST day with the properties of input images. The only property is important here is the system time start, and you can get rid of other properties. So system time start and system index. For the Landsat data we called before, for each date, one surface temperature for band number 10 is available with the system index and system time start. And also we are going to do the same process for the MODIS product. So just in order to be able to differentiate the Landsat and MODIS bands from each other, would be better to rename the final band as Landsat and MODIS. So that rename, here it is Landsat, and here we have MODIS LST. Because in regression relationship, it is important for us to define which one, MODIS or Landsat, is dependent or independent variable for the regression analysis. And also, in order to understand, in order to avoid any confusion in the next step, we need to rename the bands according to the satellite name. So now print MODIS product. As we will have too many MODIS data because of daily temporal resolution in this period, I'm gonna just print some of the data or some of the products using dot limit 10. I make a limitation to print for the results. I'm limiting our data to only 10 elements just to check that the calculation was correct, and also be sure that we have the properties we were looking. Yes, here we have the system index and system time start, and also the MODIS temperature band is also available. There it is. Back to the programming. After Landsat and MODIS provided, now we need to join them into a single collection for the corresponding date or for the same dates that both Landsat and MODIS are available. This is very important before regression modeling. So now I'm making to do the joining process. First we need to define a temporal window in which satellite MODIS data could be available within each Landsat date. So for example, I need to call MODIS data within 2 days to Landsat data or the Landsat dates. That's why here I'm making a variable as day and also set value number 2, because I need to select a period of time within that Landsat. Multiple MODIS images are available for each single Landsat frame, because using multiple daily data I can combine them for a short period of time to make a MODIS clot-free data, because the daily data are highly suffering from clot cover and also the internal noises in the satellite images. That's why we need to combine them within 2 or 3 days from for the target dates in each period to make an image with the higher quality for the regression relationship, because it's helping us to make a stronger relationship. So next, another variable is millisecond equals to Earth engine dot number day dot multiply 1000 3600 and multiply to 24. This is the equation allowing to convert the day from current unit to the millisecond format. It is very important because, as you may know, Earth engine uses the millisecond format for the temporal analysis. That's why we need to convert the day from the current unit to the millisecond format. So in the next step, I need to make a filter explaining 2 days. Here we have a 2 with millisecond format, but we need to define a filter time that explaining here 2 means 2 days, and also explaining that 2 days difference is important. So filter maximum difference is a good tool helping us to define maximum 2 days difference from each date that Landsat data is available. So make a new variable. So the name is filter equals to Earth engine dot filter dot maximum difference. So here couple of arguments available. Inside parentheses, one of the main argument is the difference. The maximum difference here is 2 days with millisecond format, assigning millisecond to the difference. So the next important argument is the left field and the right field. The left field and right field. Suppose we have, and also as you know, we have 2 image collection, Landsat and MODIS. This is the first collection and this is the second collection. Or we can say that the Landsat is left and the MODIS is right. The field are referring to the properties in which we want to say based on that property to get means. So the property in which 2 days is going to work based on is the system time start, the property explaining the date. So here the right field and the left field for 2 image collection will be system time start. So accordingly, left field equals to system time start and right field again equals to system time start. Just like that. Remove the extra parameters and back to the coding. Make another variable for joining process. There are various joining techniques in the Earth engine. Inner join, inverted, save all, save best, and every one of them has a single application in different cases. But as I want to call all MODIS data within 2 days for Landsat dates, that's important to use save all to collect all the MODIS images within the 2 days before Landsat dates and also the after Landsat dates available. So the save all, couple of arguments. The match key is the match key actually refers to the name of the properties that will include the MODIS temperature data. Here its name could be MODIS temperature. You can set any other name you want and get rid of other arguments here. So now all the input parameters are available and I want to do the joining process easily. A new variable join collections equals to Earth engine.image collection. I want to make a collection format for the output. So equals to, so here get join first. Join is the main tool that we are going to use to join these 2 products, Landsat LST and MODIS. Dot apply. The join is supposed to apply on Landsat and MODIS. We have 3 arguments here. The primary image is Landsat and the secondary is MODIS. As you remember, left field, right field, primary, secondary. So, and also the MODIS temperature is the name of the property for secondary that we'll show you in the next step. Based on what condition we want to apply join process on these two image collections. The main condition that we defined already is the maximum difference filter. Just copy and paste it. And now I'm printing join collection. Run the code. So there is something has problem here. One letter was missed. So as you can see, we have 118 elements. So because we had 118 Landsat data, one of the images may be missed because in the one specific date we had no corresponding image between Landsat and MODIS. So here for each date we have one LST for Landsat. But if you go to the property for each Landsat data, you can see that there is a new property as MODIS temperature. Here we define the MODIS temperature, and as you can see, the MODIS data are available within 2 days for the Landsat data we have. If you want to see the dates correctly, the best option, for example here, maybe in the description I can show you very well. Yes, here we have a system index. The Landsat image is for June 8, but you can see the MODIS dates also. The same date from the MODIS side, and the next MODIS image is for 1 day after the Landsat data, and the third one is related to 1 day before the date we have the Landsat data, and the next one is, for example, 2 days after the Landsat data is available. Why? Because the maximum difference is 2 days. 2 days before and after the Landsat data, we can collect the MODIS images because I want to get a maximum value for all these MODIS data to produce a clot-free with less noise image for the MODIS site data to prepare the higher quality MODIS images for the regression relationship. Or in another date, as you can see, again we have 4 elements for MODIS temperature. The Landsat data here is back to, for example, February 6, and then you can see 4 MODIS data is available for February 6, same date, 1 day after, and then 1 day before, and finally 2 days after. So, and also it can be varies from one date to another date. Maybe 2 days earlier for this product was not available, and also to use them here because we used couple of filters, and also a couple of filters here for the Landsat data to only focus on the Landsat dates in which cloth cover was very low. So, and in the next part, I'm gonna get a maximum value from MODIS temperature data to produce a single MODIS temperature product with the lowest cloth cover and noises possible. So to do this, make a new variable as a final collection. The final collection equals to get join collections images, and then import them into a function in which each input image named as a img here, and now the code make a new variable for the MODIS data equals to from Earth engine.image collection from images from each input image. As we have the MODIS data as a new property, not as a band, I'm using .get here. .get all images under MODIS temperature label or MODIS temp, then convert them as an image collection to an image collection and calculate the maximum value for that images. So finally, code returning IMG, the Landsat data, the Landsat LST with a new band that is MODIS LST data. So if I print the collection now in the right panel, again you will see a new collection with the same number of elements, but the difference is the number of the bands. One band added to the Landsat data for each date that is related to the MODIS cloud-free temperature product that we're gonna use for the regression analysis in the next step. So the data is prepared and everything is ready for the modeling in the next part. Let me to make a bigger space for coding. Yes. Make a new variable as model equals to get all prepared data from collection variable first, and then import them or bring them into a new loop structure to apply a new calculation using function. Each input element named as an IMG here, and now I need to separate bands into, or I need to split bands into different variables. So for example, the MODIS variable equals to, from input image, I'm selecting the MODIS band. Then for Landsat, a new variable dot select the Landsat band. So for regression analysis, we need to have, for the linear regression analysis, we need to have one constant band that is necessary for calculations. Constant equals to EarthEngine.image.constant, an image with value number 1 in all pixels created. So now we need two variables, dependent variable and independent variable. The independent variable for the linear regression shape equals to combination of MODIS temperature and constant band. Another variable is dependent variable. Dependent variable equals to Landsat, and finally the function returning bands according to the orders. Between orders we have for independent and dependent bands. The order is like this: first independent bands and then dependent bands. First we have MODIS temperature, then constant as independent variables, and then we have the dependent variable. So finally, to calculate the coefficient in this relationship, dot reduce EarthEngine.reducer dot linear regression. Two dimension we have x and y. The x or independent variable including two bands, the MODIS and constant. The y or dependent variable including one image or Landsat or dependent variable. So now print the result first. Print model. The output is a one image with two bands. The coefficients and residuals. So coefficients including two dimension. The first dimension is gain, and the second dimension will be the offset. So In order to get the gain and offset value from the coefficient, you need to make a new variable. So model gain equals to from model dot select from coefficients dot array get. As it has array structure, we need to use array dot array get to get the first dimension. For the model offset, we will have model dot select from coefficients dot array get, but this time selecting the second dimension. Gain and offset created. These are the coefficients or the values that we're gonna use in linear equation to convert the MODIS 100 or the MODIS coarse spatial resolution temperature to 100 meter. The gain and offset are important things that we need to have for our predictions. These are the values that helping us to predict MODIS with 100 meter spatial resolution in this case. So make a new variable. For example, the main variable was including Landsat and MODIS cloud-free data is collection. So here I'm using collection to test the MODIS temperature data with the higher spatial resolution using linear regression. So a new variable is MODIS 100 meter equals to from input collection dot map, make a new function, each input image consider it as an IMG. So now I'm gonna select the MODIS variable img.select. This is the MODIS temperature with 1000 meter spatial resolution. So then another variable is MODIS sharpened. MODIS sharp equals to get MODIS with 1 kilometer spatial resolution dot multiply to the model gain. This is a linear regression, and then dot add the model offset value. There it is. So the function returning the MODIS with 1 kilometer spatial resolution with sharpened MODIS with 100 meter spatial resolution. So, and rename it to, for example, MODIS 100 to get better understand to know that how when we are using 100 data, when we are using 1 kilometer data. So with the properties of input images. So save your code and print the new MODIS data with 100 meter spatial resolution. A new image collection we have with 2 bands. This time one of them is 1 kilometer MODIS data and another one is 100 meter spatial resolution data. So to get better understanding and insight about the quality of model and the quality of prediction, we can use map.addLayer to visualize the output. MODIS 100 meter dot 2 bands, and then clip it based on the region of interest or geometry. Leave the visualization empty and the name is MODIS temperature data, and use the false to avoid automatic visualization. So save your code and run it again. We have focused on the study area first, and then the final result is ready. So go to the layer setting and select a date randomly. For example, this is 100. This is MODIS with 100 meter, and this is the image for September 15, 2014. And also, I'm gonna visualize it through the stretching technique. After stretching applied, check the MODIS on to see the final result. Apply, and the final, this is the MODIS image with 1 kilometer spatial resolution, as you can see. And now we can see its quality with 100 meter spatial resolution. The predicted LST data with 100 meter. Apply it. As you can see, this is 100 meter spatial resolution for MODIS LST data. So, if you want to apply this equation on daily MODIS data, it is also very simple technique. Just call the MODIS LST data and apply the apply the equation. So here I'm gonna call the MODIS daily data here we had. For example, I'm making a new variable for example, MODIS sharp or MODIS 100 or MODIS temperature 100 with daily temporal resolution. Get the daily MODIS data first, and then I'm gonna filter a cloud-free period to see the best quality because when you are working with the cloud-free data, the model works better and the quality of estimation will be higher. But if you apply your equation or the linear model in the cloud images, definitely you will see with the you will face with the lots of errors and distortions in the final result. .filter Earth engine .filter calendar range. For example, I'm gonna call the data only for July because the July is a cloud-free time, at least in the region I'm working. You can choose any date or any month that's working for you with a cloud-free condition, or it depends on your application. I'm using July not only because of the cloud cover, because the vegetation cover is also higher in the region I am working. So, and then the calendar field will be month, and make a new function for each image to apply the linear regression. The function returning each input image multiplied to the model gain, and add to the model offset. Map.add layer to see the final result. MODIS temperature with 100 meter .two bands .clip it based on the geometry. Leave the visualization parameters empty, and the layer name is MODIS with 100 meter, and use the false at the end. Run the code and save it before. Here we have the MODIS data with 100 meter spatial resolution. Randomly you can select a date, and also you can have the 100 meter and 1 kilometer product together. It's very simple. image img, return img.advance to have both of images, and I'm renaming it to sharpen it. Now for each date we have both of versions, 1 kilometer and sharpened data. For example, this is July 2013, July 26. The original image is like this, with 90% stretching. Click on apply and check it on to see the original image for this date with 1 kilometer spatial resolution, and the sharpened version for the same date with the 90% spatial with 90% stretching will be shown here. Let's apply. This is the quality of estimations. Although we have some sort of pixel effects in the output, but you need to know that this is inevitable in the processing. When you are improving the spatial resolution through the regression modeling, you will have such kind of impacts in the final results. If you want to have some palettes or some color table, it's very easy to define the color with to define different colors for a range of temperatures you will have. For example, I'm defining 3 colors, blue, white, and red here, and then through the apply you will see the multicolor output that's showing a higher temperature with the red and lower temperature with the blue. I hope you liked this tutorial as much as I did, and also if you had any question or any problem regarding this code, first you need to compare yours with mine. My code is also attached below this video in my YouTube channel in the description box, and also if problem still exists, you can reach me out in the YouTube channel and I will try to help to solve your problems. Thank you for your attention.